G'day, it's Richard Maher again from Mars Classes. This video we're going to have a look at magnetic flux density, or in essence the indication of the magnetic field strength. But to do that we're going to recap some of the other stuff that we've looked at previously. So let's have a look at gravitational fields. Now when we represent a gravitational field, we draw field lines that indicate the direction of the field, and they will be travelling from positions of high gravitational potential energy to positions of low gravitational potential energy. And if you placed a mass within that field, spontaneously that mass can only move in one direction, and that is from the position of high to the position of low gravitational potential energy. And then we looked at electric fields, and again we have field lines that indicate a direction of the field, and again they go from regions of high electrical potential energy to regions of low electrical potential energy. Now you place charges in that field. If they're positive or if they're negative will determine which direction that they will travel. A positive charge will always move from high potential to low potential, and the negative charge will move in the opposite direction, that is from a low to a high potential. If you have many charges moving, you're going to get an electrical current. So what we'll do is have a look at how convention has been used to describe these currents. And remember, in a previous video we looked at conventional current. Now we know that electric fields are defined the direction the positive charge will move when placed in the field. So the convention was that the current is the direction that a positive charge will move as well. So when we look at, say, a common cell that you might use, we have a positive terminal is at the positive electrical potential, the high electrical potential, and the negative terminal is at the low electrical potential. If we connect those two things with a conductor, we'd say that a positive charge would flow from the high electrical potential to the low electrical potential, and that would be the direction that conventional current would flow. We do also know, however, that positive charges don't flow in the wire, so they're not going to be flowing. So if we're going to describe a current, and the current is when charges are moving, and if the current has been defined as the direction that charges will move when they move from high potential to low potential, that's going to be the opposite direction to what an electron would actually flow. But again, convention says that we're looking at positive charges when we're considering current. Okay, now let's move on to what happens when a charge does actually move. Now Maxwell recognised that when you jiggled or moved a charge, the electric field lines around that charge would also move as it moved. And if you can move or oscillate a charge enough, you can distort those electric field lines until they form loops, and we call those lines magnetic field lines. So if we had a charge moving along in one direction, and all the electric field lines were being distorted as it moved and form concentric rings, those things we call magnetic fields. Now if it's not just one charge moving, but we have multiple charges moving along a wire, those multiple charges will set up a magnetic field around that wire, which will be concentric circles around that wire. Now these images I'm showing, these animations that I'm showing, are pretty hard if you're going to try and represent with pen and paper. So we've come up with some conventional means of representing directions of field lines or directions of currents. And the way we do that is we consider, say, a dart. And if you look at the dart, but if you look at it end on, you'd see at the end coming towards you, it would look like a circle with a dot in the middle, and the end going away from you would look like a circle with a cross in it. Now that's how we represent current, electrical current. If the electrical current is coming out of a page or a screen, we represent it as a circle with a dot in it, and if it's going into a page or a screen, we represent it as a circle with a cross in it. Okay, so let's have a look at the top view of an electrical conductor with the current coming out of the screen. Now if the current comes out of the screen, remember we said that these moving charges will set up concentric rings of magnetic field. How do we determine the direction of that field? Well, what we do is we use our right hand grip, and what we do is we have our thumb, which will represent the direction of conventional current, and our fingers will curl in the direction of the magnetic field lines, which will be formed around that current carrying conductor. So if you have a look on the image I've got at the top of the page, you've got concentric circles, and the electrical current is coming out of the page, and the magnetic field lines have a direction which is anti-clockwise. So let's have a look at that side on, not end on, that electrical conductor. So if we look side on and the current is coming up the page, and we use our right-hand grip rule. On the left of the conductor, the magnetic field will be out of the page, and on the right of the conductor, the magnetic field will be into the page. Now you'll notice the convention we use to represent direction of fields is again the dot if it's coming out of the screen or the page, and the cross as it's going into the screen or the page. But this time we don't put a circle around it. The circle around it represents that it's a current carrying conductor. Now of course the field wouldn't be just one set of concentric circles. There'll be a whole lot of concentric circles all going around that whole conductor. And again, if we looked at the current in a conductor that's going into the page, and again we use our right-hand grip rule, we can find that as it goes into the page, sorry, I'll go back, goes into the page, we end up with a magnetic field which is now clockwise. So what I'm doing is I'm pointing my thumb into the screen or the page. My fingers on my right hand will curl in the direction of the magnetic field. So side on, we get a representation like that, with again the crosses and the dots representing the field going into the pages across, magnetic field going into the pages across, and the magnetic field coming out of the page is a dot. And again, there'll be lots of concentric circles. Okay, so you might notice that when I've represented those concentric circles, I do have them a little bit closer together, closer to the conductor and further apart, further out. Now, it was Ørsted who discovered that there was a magnetic field around a straight conductor, also made some observations about the strength of the field. So when he looked at that, this representation I've got here is the left-hand current carrying conductor is carrying a smaller current than the right-hand conductor. And you look at how I've represented the magnetic field lines there, they're a little bit different. And Ørsted also recognised that too, and he saw that the larger the current, that you actually ended up with denser field lines, and also that they reached further away from the conductor. Now when we've looked at gravitational fields, we've said that, or magnetic fields we'll look at later on, the density of field lines indicates the strength of the field. So the larger the current, the denser the lines, that means the stronger the field. So there's a proportionality between B, which is the symbol we use for magnetic field strength, and I, the symbol we use for current. He also noticed that the density of the field lines decreases the further you get away from the conductor. So when we look at that, the greater the distance from the conductor, the weaker the magnetic field will be. So he's recognised there's an inverse relationship between magnetic field strength and R. That's the radius of the circle of the magnetic field, or the distance from the conductor. So when we combine those things, we see that the magnetic field strength is actually proportional to the current divided by the distance from the conductor. Now that's proportional. If you want to make it equal to, you have to multiply it by a constant value. We could use K, but actually what we do is we use a symbol for a thing called permeability, which is mu, and we found that if it's divided by 2 pi, mu on 2 pi times I on R will give you something that actually gives you the magnetic field strength. Now, when we look at that equation that I had previously, you'll more often see it written as mu 0 I on 2 pi R. Now, what the mu was, as I said, was a symbol for permeability, and that's how well that a material will allow a magnetic field to be supported within it when the magnetic field is formed. The mu 0 represents the permeability of free space, a vacuum, and essentially air is pretty close to that. So we'll be using this value mu 0 quite a lot. And if you put mu 0, which has a value of 4 pi times 10 to the negative 7 Weber per ampere meter, if you plug that into mu 0 on 2 pi, you get a value of 2 times 10 to the negative 7. So more often than not, you will see the equation that shows the magnetic field strength as represented as 2 times 10 to the negative 7 I on R. Now that calculation we'll be performing in quite a few calculations as the year progresses. It's a pretty straightforward sort of common sense thing, isn't it? The further away you are from the conductor, the weaker the field will be, and the bigger the current, the bigger the field will be, or the stronger the field will be. Okay, look, I'll leave it at that for now, and we'll meet again next time.